Right. This is a talk on large-scale vortex formation in protoplanetary disks. This talk was delivered at Princeton and Cornell recently. I'm going to present the Cornell version here, but the Princeton version is quite similar, and you can find the PDF for that on my website. I want to talk about purely hydrodynamic instabilities in protoplanetary disks. Um, and this is going to be a summary of work I did in my first year at CETA in Toronto. So I want to start off with some observational results. These are observational images of transitional disks. So these are disks which have holes in them. And the feature I want to point out here is that these disks do not appear to be axisymmetric. So in these examples here, we see these blobs around the disk, and also in this image here. So I think it's important to understand the origin of these structures and possible implications on the disk evolution and planet formation. This is a cartoon of a theoretical model of a protoplanetary disk, and some theoretical models of protoplanetary disks have a region called the dead zone, where the magnetorotational instability is inefficient in transporting angular momentum. So there's this interest in looking for purely hydrodynamic instabilities in the dead zone. Now, if you have a structured disk like this, you might expect at the boundary between a dead zone and the active region, so in this region here, to involve localized radial gradients in the disk. In that case, you can then ask, well, what are the stability properties of these localized gradients in the disk? And if they are unstable, what are the possible consequences and on disk evolution and planet formation? And to answer this question, we can start with a simple toy model. So we can just consider a axisymmetric overdense ring embedded in a smooth disk. So this density ring could represent some kind of localized feature in the disk. So you can set this up on a computer and just evolve the system and see what happens. And I've actually done this with a couple of different hydrodynamic codes. So here I've done the simulation with a Zeus code. So this is a three-dimensional self-gravitating disk, and the ring essentially breaks up into these non-axisymmetric blobs, which I'm going to just call vortices for simplicity. Now the instability comes about for the following reason. I'm going to pull up a paper, recent paper by Heloise Mayhew. So this is a paper that came out recently. And there's a very nice diagram here, figure 1. Okay, so the instability comes about for the following reason. We've got a density, some bump in the system, in this case a density bump with some localized feature. Now it turns out that around this bump radius here, we can have disturbances called Rossby waves. So these Rossby waves propagate on these gradients of the bump. And just inside the bump radius, this Rossby wave has negative energy. And just outside the bump radius, the Rossby wave have a positive energy or angular momentum. And as energy or angular momentum is transported from the inner disk to the outer disk, the inner Rossby wave becomes more negative in energy, and the outer Rossby wave becomes more positive in energy. And this leads to an instability. And the result of the nonlinear evolution of the instability is the formation of these large-scale vortices in the disk. Now, I've also done this simulation with Athena. So this is a three-dimensional disk, stratified disk in a Cartesian box. And in this particular figure here, I've actually subtracted out the background density bump. So what you're seeing here is just the density perturbation. And this result here is actually quite consistent with the cartoon I showed earlier. So we have these two disturbances on either side of the bump interacting with one another, which destabilizes the system. Just to note that there are 4 blobs in this particular figure, but this is actually not due to the sort of square geometry of the problem. The m=4 mode happens to be the most unstable mode. Okay, so we could also put in some physical process which actually creates the bump in the first place, or the density structure in the first place. And this is some simulations I've done with the Pluto code. The two examples here on the left here is a three-dimensional disk where I've imposed a viscosity jump in radius. And so I've chosen the viscosity profile such that the inner disk has a high viscosity value and the outer disk has a low viscosity value. So at this viscosity jump here we have mass buildup, and that localized structure becomes unstable, and we form these large-scale vortices in the disk. The right simulation here is a disk planet simulation where I've actually put in a giant planet, so in this case a Jupiter mass planet. In the disk, I've let it open up a gap, and I've chosen a viscosity value which is low so that these gap edges become unstable to this vortex instability. I just want to point out that the disk planet simulation here is actually a self-gravitating disk, but these blobs here, these are not gravitational instabilities. The disk is actually quite far from gravitational instability. So these vortices can do two things. One is they could transport angular momentum outwards and help accretion. But right now there's probably more interest in these vortices because they can potentially assist planetesimal formation. So these vortices tend to concentrate dust particles at their centers. So that might help planetesimal formation. But the vortex formation mechanism I'm talking about here is through a linear instability. So before talking about these effects, we should start by an understanding of the linear stability of structured disks. And I've looked through the literature, and depending on the context of the study, these instabilities have different names. I'm going to be thinking about geometrically thin accretion disks. So in this case, the modern name is the Rossby wave instability, developed by Richard Lovelace in 1999. Now, in the original RWI calculations, Lovelace considered a two-dimensional disk, non-self-gravitating and adiabatic. There's been a couple of generalizations to this framework. For example, self-gravity has been added, magnetic fields have been added, and three-dimensionality has been added as well. Now in this video, I want to extend those three-dimensional results to, first of all, to thermally stratified disks, so I'm going to use polytropes for that. And then in the second part, I want to extend it to adiabatic three-dimensional disks. So in the adiabatic 3D would be a more direct extension of the original calculations to full 3D. Now I'm going to go into the technicalities of this problem. So how do you actually attack something like this? The equation I'm showing here is one of the more general equations you can write down for the linear problem. Now the point I want to make here is that the linear problem becomes very complicated in 3 dimensions. You generally have to deal with some partial differential equation with potentially singular coefficients, and then this equation is actually complex as well. So the first question one might ask is, well, why bother with doing the linear problem, right? Because as I showed earlier, we could actually just simulate the entire thing on the computer and maybe even just add in some new physics that wasn't there in the linear problem before. But I think it's still important to do these kind of linear calculations even if they become very complicated because, well, a linear instability is a growing solution to the eigenvalue calculation, right? So it's almost a necessary calculation to do by definition. But I think the second point on this slide is most important to me because I do a lot of hydrodynamic simulations. In fact, everything I do is based on hydro simulations. But I don't always trust my simulations, right? So to me, the linear problem is really just a way to check my hydro results. So I want to start off with the linear problem for 3-dimensional polytropic disks, by which I mean the pressure field is going to be a power law function of density, with n is the polytropic index. And this relation is going to hold both in the basic state and in the perturbed state. So this thing holds at all times. And this equation replaces the energy equation. So I'm going to go through a very standard piece of linear stability calculation here. And the standard procedure is the following. The first thing we need to do is to define an equilibrium disk. So I'm going to consider a steady disk, axisymmetric, and in vertical hydrostatic equilibrium. I'm going to have a smooth disk, but I'm going to put in a density bump, a localized bump at unit radius. We can go ahead and perturb the fluid equations. I'm going to assume perturbation that have this functional form. So it's going to be a function of cylindrical radius and height, a function to be determined, and multiplied by an exponential factor which takes care of the azimuthal dependence and the time dependence here. So we can combine the linearized equations and get a single equation to describe the problem. It's a linear operator L acting on a perturbation variable W equals 0. Now W here is the enthalpy perturbation, so it's the pressure perturbation divided by density field. So W is our eigenfunction. The operator L is a PDE operator. It's very complicated. It depends on both the cylindrical radius and the height and on sigma. So the sigma is the eigenfrequency or eigenvalue of the problem, and sigma describes the time dependence of the disturbance. But actually, sigma only appears in this problem through this factor sigma bar here, which is sigma plus m times the angular frequency. So sigma bar is what we call the intrinsic frequency or the intrinsic frequency of the disturbance. So I'm going to look for a very special solution. I'm going to look for a solution where the real part of this intrinsic frequency at the bump radius is close to 0, and the bump radius is going to be a potential vorticity extremum. So eta here is the vortensity or potential vorticity. So essentially what I'm saying is the corrotation point of the mode is going to coincide with the vortensity extremum. Now this linear operator L is very complicated even if you're prepared to do the problem numerically. But we can note some interesting facts about this linear operator. The operator L only depends on the vertical coordinate through the density field. And for a polytropic thin disk, the density field has the following form. So it's the midplane density multiplied by a vertical stratification function here. So it's 1 minus z squared over h squared to some power. H is the local disk thickness. Now if we go to a new coordinate system where we normalize the height by the local disk thickness, then the density field is separable. So it looks like this. So it's a function of radius multiplied by a function of this normalized height, W here. Now W is the vertical stratification function, and in these normalized coordinates, the stratification function is 1 minus the normalized vertical coordinate squared to some power. Now the key here is to note that this functional form here, 1 minus z squared to some power, happens to be the same functional form which describes, well, it's the same functional form as the weight function for a particular set of orthogonal polynomials. I think this is pronounced Geigenbauer polynomials, and it's a generalization of the Legendre polynomials. So the only thing to take away from this slide is to note that the operator L is complicated, but it only depends on z through this very special stratification function, which happens to be the same functional form which defines orthogonality properties of these polynomials. This actually turns out to be very useful because it means if we assume this functional form for the solution, so my eigenfunction or my enthalpy perturbation, which is a function of both coordinates, is written as a series of radial eigenfunctions, WL, which takes care of the radial dependencies, multiplied by one of these orthogonal polynomials, CL, where so CL takes care of the vertical dependencies. I want to stress that this is actually an assumption. But if we make this assumption, then what we can do is we can operate on this equation with the operator L, and then we can multiply that result with another one of these orthogonal polynomials, and then we can perform a vertical integration. So that's the second line here. When we do this operation here, what you will find is that the vertical coordinate in this expression here only appears through this terms that look like this. So in other words, all the vertical dependencies come through as a term which is the definition of the orthogonality properties of these polynomials. So in summary, what I'm saying here is that if we write the solution in this form, then we can perform a vertical integration, which can be done by hand. Right? So all the vertical dependencies can be removed. So we've actually eliminated one coordinate from the problem. So we've actually transformed the problem from a partial differential equation to some ordinary differential equations. So, and once you get these ordinary differential equations, you can just put it into an ODE solver. So the summary here is that the polytropic disk problem is a very special problem because the partial differential equation can be converted to ordinary differential equations because the PDE operator depends on the vertical coordinate in a very special way. So I want to have a look at some results now. So this is actually a polytropic disk with a surface density bump, but what I plotted here is the potential vorticity, and the potential vorticity is inversely proportional to the surface density, so a density bump corresponds to a PV dip here. I'm going to look for solutions or modes which are radially localized in this dip here. What that means is boundary conditions near the inner disk edge and the outer disk edge do not play a significant role. So all the action is happening at the bump or dip in potential vorticity here. So this is the solution to the eigenvalue problem. What I've plotted here is the radial eigenfunctions. So just as a reminder, the enthalpy perturbation is being written as, in this particular form, as a radial eigenfunction multiplied by a orthogonal polynomial, which takes care of the vertical dependencies. Now this diagram here, this figure here, only plots the radial eigenfunctions, so only plots the WLs. In the figure it's actually labeled S, but it's the same thing. I'm only interested in the region close to unit radius, because that is the region where vortices is going to form eventually. In this case, we see the solid line here, which is the W0, which represents the two-dimensional component of the solution. Now this component is actually much larger than the dotted line, which is W2, and that is the first 3D component. So essentially, the 2D component is much larger than the 3D components around co-rotation. And indeed, the instability is actually essentially two-dimensional. The growth rate is about 10% of the angular frequency, and it's actually the same whether you do the problem in 2D or 3D. So the problem is, so the instability is 2D. So if we look at the dotted line here, then you see that as you go towards unit radius, its magnitude goes down. So the 3D component gets damped out as you go towards co-rotation. Now, if you look into the literature, you can find rigorous analytical arguments as to why the 3D component is much smaller than the 2D component at co-rotation. But I wanted to look for for one-line explanation as to why this happens. And I'm going to appeal to this expression here. So this is the vertical velocity perturbation, which you can derive from the linearized equations. And the vertical velocity perturbation is essentially the ratio of the vertical derivative of the enthalpy perturbation to the intrinsic frequency of the mode. Now, the intrinsic frequency of the mode, sigma bar, is actually effectively zero around co-rotation, so by definition. So from this expression alone, I can see that, okay, if sigma bar is very small, then I would expect dw dz to also be small. Otherwise, my vertical velocities would explode. So from this expression alone, it makes sense to me that W2 is much smaller than W0. So the 3D component is a small perturbation to the 2D solution. This is a plot of the perturbed velocity field in the midplane. I've plotted, and I'm focusing my plot around an overdensity or overpressure. And the perturbed flow, the sense of rotation of the perturbed flow here is actually anticyclonic. So the sense of rotation is actually opposite to the background rotation around the central star. Okay, now the 2D component is much larger than the 3D component of the solution, but the 3D component is not exactly zero, and that's the point of doing this 3D problem, to find out what that vertical velocity is. So what I'm going to do in the next slide is I'm going to plot the meridional plane, or the RZ plane, at this azimuth here. And so this is the result, and most of the flow is actually horizontal, but at rotation, at the unit radius, is actually upwards. Now this upwards motion has actually been seen in hydrodynamic simulation, so let me just pull out another paper by Heloise Mayhew, another recent paper. So this is a numerical simulations paper, and what they found in this case was, so they simulated this Rossby wave instability in 3 dimensions for a polytropic disk. And they indeed, what they found was this figure here. What they found was, so this is the streamline or flow pattern of an anticyclonic vortex. So they found upwards motion associated with anticyclonic vortices. And that is consistent with this picture here from the linear problem, that there is upwards motion at rotation. Now what I found from the linear calculation is that this upwards motion depends on the equation of state. So these are 2 more calculations done with, first of all, a n equals 1 polytrope. So the previous slide was a n equals 1.5. And the lower plot here is a vertically isothermal disk. So that's actually n equals infinity. So the magnitude of this vertical flow at rotation depends on the equation of state, and is such that the magnitude decreases as you make n larger. So in other words, as you make the fluid more compressible, the vertical flow actually diminishes. Now this actually makes sense to me because suppose I'm holding a piece of highly compressible fluid, so like a n equals infinity polytrope, then as I try to increase the local density, that's what the instability is trying to do. So I'm trying to push material towards unit radius, but because it's very compressible, the density at unit radius can just increase, no problem. But if the fluid is not very compressible, then as I try to push material towards rotation, I'm trying to gather more stuff, then because it's not as compressible, then that would induce a vertical flow, so the fluid is pushed upwards. So this actually kind of makes sense to me. So in summary, for the polytropic disk problem, now the polytropic disk problem can be treated in a special way because the vertical dependencies of the linear operator is very special. So basically, I've used a spectral method in this problem for the polytropic disk problem, where I've converted the partial differential equation to ordinary differential equations. This is a spectral method, and it's nice because mathematically it looks quite nice. It's also good because you're solving a problem in spectral space. That means you can immediately see the different contributions to the solution. So for example, in this case, we saw that the instability is essentially 2-dimensional. But turns out that this is not a very economic method of solution if you're interested in numerical answers. Because first of all, it involves a lot of work. Working with these polynomials is not simple, and it took me a while to get the equations right. But I think the more limiting factor of this method is the fact that we do not have flexibility in vertical boundary conditions. What I've actually done in this problem is I've assumed the upper disk boundary is at the zero density surface, but there is no reason why the upper boundary should be at that surface. Right? So essentially, what I wanted was a simpler method of solution, but also at the same time I wanted freedom to impose vertical boundary conditions. So that brings me to the second part of this talk, where I want to extend those 3D linear calculations to three-dimensional adiabatic disks. Okay, so I'm actually going to consider the same background disk before, so I'm still going to consider polytropic equilibrium disks. So here the pressure is a power law functional density. I've written the power law index here as big gamma for simplicity. I'm now going to include an energy equation which says the entropy is conserved following a fluid. And the entropy is pressure divided by the density to small gamma. Small gamma is the ratio of specific heats. And I'm going to consider this regime where small gamma is bigger than big gamma, so that means I'm in a convectively stable disk. And that means if I'm considering a density bump, then I'm actually also considering entropy dips. So we can go ahead and linearize all the fluid equations and combine them. In this case, I ended up with a pair of partial differential equations. The operators v1, v2, v1 bar, and v2 bar are PDE operators. W is the pressure perturbation as before, so it's delta P over rho. Q is the density perturbation, so it's the density perturbation divided by the background density multiplied by the sound speed squared. And so from these two definitions here, it's quite natural to define the entropy perturbation as the difference between W and Q. So the difference between pressure perturbation and density perturbation is the entropy perturbation. Now, before we look up numerical methods to solve these partial differential equations, I think it's useful if we have a qualitative sketch of the solution before we solve the problem. Because I'm doing this problem numerically, having an idea of what the solution ought to look like will help us judge whether or not the numerical answer makes any sense. Now, in the horizontal plane, I'm looking for anticyclonic motion associated with overdensities, because well, that is actually a sort of defining characteristic of the instability. But at this point, I don't really know what to look for in the meridional plane, so right now I can't really tell whether my numerical answer is right or not. So what I want to do in the next couple of slides is to sort of sketch out the qualitative features of the solution that we can expect and we can use to judge whether or not our numerical answers make any sense. So I want to consider a quantity which I've defined to be S bar, and it's the density perturbation minus a number multiplied by the pressure perturbation, and this number is gamma over gamma. The second equality here comes from my definition of the entropy perturbation. So it's this factor here. So S bar is this, and we can think about we can go back to basics and think about what does the instability do. Well, it tries to make overdensities, right? It takes an axisymmetric ring and turns it into a non-axisymmetric structure. So we have these non-axisymmetric blobs. I'm going to focus on a overdensity or overpressure here. So this means I'm considering a region where W and Q are both positive. Next thing I need to figure out is what is the sign of the entropy perturbation associated with this overdense blob here. And I'm going to go to the midplane now. And in the midplane, because I'm considering a density bump, that means I'm considering an entropy dip. So we have an entropy dip here at the bump radius. And we can think about, well, what happens in the perturbed state? Well, the instability is trying to make overdensities, right? And I can make overdensities by putting more stuff at unit radius. But what this means is because entropy is conserved following a fluid, you would actually be moving higher entropy material towards a location where the background entropy is lower. So the local Eulerian entropy perturbation is actually positive in this location here. So if we go into midplane, then we can then say, okay, at the midplane, at this overdense blob here, WQ are both positive by definition, and S at this point here is probably positive as well. So in the next slide, I'm going to go into the midplane, and I'm going to go to this azimuth here and try to sketch out the solution in the meridional plane. Okay? So here's the meridional plane at that azimuth. And this point here is the point I was referring to before. So here, the pressure perturbation, the density perturbation, and the entropy perturbation are all positive. And so from this equation here, you can deduce that S bar is actually negative at this point. Because, well, W is positive, right? And this factor here is actually negative because gamma, small gamma, is bigger than big gamma. So 1 minus that is less than 0, multiplied by W, which is positive. So the first factor here is a negative contribution. S itself is actually positive at this point. So this contribution here is negative as well. So both contributions are negative, so S bar is negative at this point here. Now it turns out that the upper disk boundary condition I'm using implies S bar is 0 at the top of the disk. So that means S bar goes from a negative number here to 0 up here. So the simplest thing is to say, well, S bar is probably negative or 0 along this dotted line here. And then we can think about, well, what happens away from this dotted line here? Well, I'm looking for radially localized perturbations, right? So as I move away from this dotted line, I'm hoping the magnitude of perturbations would go down. So we can put in these annotations. So S bar should be decreasing as I go away from this dotted line. So here's our sketch. And what this sketch tells us is that S bar is probably a negative number in this region, and it probably has a local minimum at the midplane at the bump radius. So this is a comparison between our sketch at the top, and the bottom is the actual numerical calculation from the eigenvalue problem. And I think as far as guesswork goes, this comparison is quite good. Now, I haven't really said why I'm interested in S bar. I'm interested in S bar because it turns out that if you write down the linearized equations for the problem, and S bar actually contributes to vertical motion. And if S bar is not uniform in this plane here, it turns out that non-uniformities of S bar in this plane can lead to vorticity production. So it's a baroclinic source for vorticity, in particular the azimuthal component of vorticity. So what that means is that if S bar is not uniform in this plane, then you can actually get generation of vertical motion in this plane due to baroclinity. So in fact, so the point of this exercise, I wanted to go through it in some detail because I wanted to demonstrate that in some cases you can actually sketch out or extract a fair amount of information without actually solving anything. We deduced this sketch here without any reference to, essentially without reference to fluid equations. So you could actually go a step further and use this sketch and the fact that these things act as source terms to deduce how does baroclinity contribute to vertical motion, and how does baroclinity contribute to vorticity production. But at some point you do actually have to solve the linearized equations. And I found the pseudo-spectral method to be quite useful in this problem. I'll just quickly explain what I mean here. So in the pseudo-spectral approach, what we do is we have some domain in which we want to solve the problem in this case the RZ plane. The first thing is we discretize the domain in the radial direction, so these lines here represent discretization in radius, and along each of these lines, let's say the ith line here, I'm going to assume the perturbation is a linear combination of basis functions. So that's the equation here. Now these basis functions can be any complete set between -1 and 1, but I think it's conventional to use Chebyshev polynomials, and that's what I use here. Once we write this equation down, then we can approximate radial derivatives of a variable by just finite differencing across different lines. So for example, dWdr at for this line here is the difference between this line here and this line here. And we can perform vertical derivatives exactly because I've made the assumption here. Anyway, the point is, once we do this, then we can evaluate the original PDEs, that's these things here, at a set of grid points. Once we do that, if we do that, then what we will do is convert the original PDEs to matrix, to a set of matrix equations. So these are now matrices. V1, V2 are matrices. V1 bar, V2 bar are matrices, and W and Q are vector representations of these pseudospectral coefficients. Anyway, the point is the pseudospectral method converts the PDE to a set of matrices, and once we get these matrix coefficients, then we can feed it to a matrix solver, and it will give us the solution. So the key difference between the pseudospectral method and the previous spectral method we use for the polytropic disk problem is the fact that here I've actually left in the vertical dependencies. So I've not done a vertical integration here. So the good thing is that now we can actually impose vertical boundary conditions as we like. So all we do is that everywhere in the interior we solve the PDE. So the operator U will represent the PDE. But at the upper disk boundary here, for example, we will replace the PDE by boundary conditions. So the matrix coefficients in U at the upper disk boundary will be modified to describe whatever boundary conditions you want to do. So I've considered things like no Lagrangian pressure perturbation at the upper boundary, no velocity perturbation at the upper boundary, or no velocities perpendicular to the upper disk boundary. And I've made a simplification of this problem where I've assumed the upper disk boundary here is actually a constant fraction of the local disk thickness. But in principle, you could define an arbitrary surface shape for the upper disk boundary. So anyway, let's look at some solutions. This is a non-homotropic disk. So this is a disk where the gamma describing the background structure differs from the gamma for the thermodynamic evolution. So non-homotropic here means the entropy is not uniform. So for example, the entropy varies with radius, and it also increases with height here. What I've plotted here is the sum of the epicyclic frequency squared plus the buoyancy frequency squared. And this increase in this quantity with respect to height is due to n squared increasing with height. So anyway, this is the background disk we're interested in, and this is examples of the eigenfunction from the eigenvalue calculation. Now I'm actually solving the problem in physical space here, so these are plots of the perturbation in physical space. I have the pressure perturbation, the density perturbation, and difference between them is the entropy perturbation. And these curves are actually pretty similar to what we found for the polytropic disk problem, where most of the action happens near the bump radius here. But I thought it was interesting to know that the perturbation magnitudes actually increases away from the midplane, which is different to the previous case, where in the polytrope there's actually very weak dependencies with respect to height. So these are plots of the perturbed velocity field in the midplane on the left here, and near the upper disk boundary on the right here. And the color here is the entropy perturbation. And the flow pattern is actually very similar to the polytropic disk, namely it's anticyclonic. Right? But if you look a little bit closely, you might find that the center of this anticyclonic motion is somewhere here in the midplane, but it is shifted a little bit downstream as you go away from the midplane. So it looks like as if the vortex is being tilted with respect to height. Okay, right. So this is a plot of the velocity field in the meridional plane. And this is taken at an azimuth which cuts the center of these vortex perturbations. So the point I want to make here is that the vertical flow here is actually very different to the polytropic disk problem, polytropic disks. So in this case, we actually get vertical motion in the meridional plane, and this is probably due to that baroclinity, right, caused by the fact that grad P and grad rho are not do not coincide. So this is quite interesting. What I'm going to do in the next plot is I'm going to plot the vertical velocity at unit radius as a function of height for a couple of different cases. So here's the result. So this is the vertical velocity as a function of height away from the midplane at that radius, at unit radius, at bump radius. And I just want to look at the solid line here and the dotted line here. So the solid line is the case where both gammas are the same. So this is a disk with uniform entropy everywhere. And the dotted line is the case where small gamma is a little bit bigger than big gamma. So it's a non-homotropic disk. But actually, if I look at these two curves, I can see that there's a noticeable difference between the solid line and the dotted line, right? But the difference between these gammas are actually not very big. They differ by less than 10%. Yet I see a noticeable difference between the vertical velocities. So I guess one question you might ask is, well, is there anything that might cause a sort of more fundamental difference between a disk where entropy is strictly uniform, like the solid line, and a disk where entropy is a little bit non-uniform, like in the dotted line? So I looked into the literature and came across a review article by Cato. This is a review article on thin disk oscillations. And from this article, you can get an expression for the vertical velocity for thin disks in the case where the Brunk-Weisler frequency, or the vertical buoyancy frequency, is non-zero. In this case, there are two contributions to the vertical velocity. The first term here has a dWdz here. Now, W is the pressure perturbation. So this term is a contribution from pressure forces, so pressure gradients essentially. And the second term here is just proportional to W. And it also depends on dP dz, which is basically gravity, vertical gravity. Right? So the second term here is actually a buoyancy term. Now this first expression here is very different to the case where if the vertical Brunk-Weisler frequency is identically zero. If this is the case, then the vertical velocity, delta Vz, is given by this expression here, roughly speaking. And these two are very different, right? Which suggests to me that, vertical velocities have a different origin between homotropic disks, so that's where Nz is 0, and disks which are non-homotropic, which Nz is not identically 0. Now if I look at the first equation here and I compare the magnitude of the pressure force term and the magnitude of the buoyancy term, then that ratio is proportional to omega squared over Nz squared. And omega is not a function of height in my models. But Nz actually increases away from the midplane. It actually diverges in my models. So away from the midplane, eventually, this ratio becomes quite small. That means buoyancy becomes more important as you go away from the midplane. So I think that means the origin of vertical motion is very different between homotropic disks, so where uniform entropy, where entropy is uniform, and disks with non-uniform entropy. Now, so that's interesting to note, but the biggest application I have for this linear calculation, as I said from the very beginning, is just to check my hydrodynamic simulations. Now this is a comparison between a Zeus simulation and the calculation from a linear stability problem. And this is a isothermal disk, but evolved adiabatically. And I focus these plots on one of these vortex perturbations, and I'm quite content with this comparison here. So I have anticyclonic motion associated with overdensities here. And the agreement is also quite good in the meridional plane. So this is a comparison between meridional flow between the Zeus calculation on top and the linear code on the bottom. In both cases, I have this I have this vortical motion in the meridional plane. Okay, and the eigenfrequencies actually agree pretty well as well. Now, okay, so that's essentially most of what I wanted to say. I want to now jump a little bit into a slightly different issue, and that's self-gravity. I haven't talked about self-gravity in this problem, but we ought to talk about self-gravity because these vortices, at the end of the day, they are just these overdense blobs of fluid going around the disk, right? And also, in fact, the key quantity which determines the stability property of structured disks is the potential vorticity, right? Eta here. And the key quantity which describes gravitational instability is the Truman parameter, Qt here. Turns out that these two quantities are actually more or less the same thing. Right? They can be written in terms of each other. On this slide, what I wanted to show was what I want to discuss here is what is the effect of self-gravity on this Rossby wave instability. And the result is that the self-gravity actually stabilizes this instability, and the short explanation is summarized here. So we can write down the linearized equations for the problem with self-gravity. So the linear operator acting on some perturbation variable, giving us the density perturbation. Now from this linear equation here, we can derive an integral relation, which looks like an energy equation. So in this case, we can derive an equation which has this form here, and if we have a instability or disturbance associated mostly with this potential vorticity extrema, then this relation here can be simplified to this relation here. So on the right-hand side, I have two contributions to the energy. I have a thermal part, which is positive, and I have a gravity part, which is negative. On the left here, I'm saying, okay, most of the disturbance comes from the potential vorticity extremum. So the energy here is balanced by the disturbance at that extremum, and the sign of the left-hand side depends on whether or not I'm at a potential vorticity maximum or minimum. If I'm at a potential vorticity minimum, and that's the case observed in numerical calculations, then the left-hand side should be positive. That means I need to have the right-hand side positive for this rough balance to make any sense. And that means gravity must be sufficiently weak. So if gravity is very strong, then the right-hand side is negative. In that case, it doesn't make sense to balance this negative quantity with with disturbances at a potential vorticity minimum. So the fact that self-gravity stabilizes the Rossby wave instability can be interpreted as a consequence of energy balance. And this is a numerical calculation of the Rossby wave instability. In one case, the dotted line without self-gravity, and in the solid line with self-gravity. And what's plotted here is the growth rate of the instability. So the self-gravity growth rates are actually smaller than the non-self-gravity growth rates. So self-gravity actually stabilizes this instability, which is a very counterintuitive result. Okay, last thing I want to talk about is some recent work I've been doing. Oh right, before we look at that, one extra slide on self-gravity in 3 dimensions now. When we go into 3D, we also have vertical self-gravity, and these are simulations I've done with the Zeus code. In this case, these are plots in the meridional plane through one of these vortex blobs. In the upper diagram is a case with in the case without self-gravity, and the bottom plot is the case with self-gravity. Now this model actually has a minimum tumor parameter of 8 when I start off the simulation, which normally one would consider to be non-self-gravitating. But it's clear from this plot that in the perturbed state, self-gravity does make a difference. So the point I wanted to make with this plot is that I can start off a simulation, say qt equals 8, which is justified to be non-self-gravitating, but you can't guarantee that is still valid in the perturbed state because I have an instability which creates overdensities. So I think self-gravity should be included in these type of calculations. So calculations which look at large-scale overdensities. Okay, so last thing I want to talk about is some recent work. And recently been doing some numerical calculations, numerical simulations, looking at how does this vortex instability operate in the layered accretion disk scenario. And the motivation comes from the fact that the linear stability problem is giving me solutions that look like this, right? It's giving me solutions where the perturbation extends throughout the vertical column of the fluid, so it's a global instability in the vertical direction. So it's not obvious to me that what will happen if this instability can still operate if I put in some complicated physics at the upper boundary of the disk. Right? So, for example, if I put in a active zone or a actively turbulent layer on top, what would happen to this instability? So I've been doing these numerical calculations with the Pluto code, and I just want to showcase one example here where I'm considering a planet disk system. So in this case, I have a 3-dimensional non-self-gravitating disk, and I put in a giant planet in the disk, and I let the planet open up a gap. And I'm imposing a viscosity which is quite small, an alpha viscosity of about 10 to the minus 4 in this problem. And in this case, the gap edges become unstable to this Rossby wave instability, and it leads to the formation of a large vortex at the gap edge. Now this picture here is actually quite a standard, well-established result from people doing disk planet simulations, that if you put a giant planet in a low viscosity disk, you will get vortices at gap edges. So the question I had was, well, what if I put in a viscosity value or viscosity profile that looks like this? So I've got some low viscosity disk near the midplane, but away from the midplane, I'm going to boost the viscosity up to 10 to the minus 2. Now for reference, the more typical value for viscosity that's adopted in the protoplanetary disk is alpha of about 10 to the minus 3. So I've got a midplane which is lower than that value in the atmosphere, which is higher than that value. Anyway, the question is, if I put a giant planet in the midplane here, what would happen? Can I still get vortex formation? And this is a result. Well, something is happening at the gap edges, but certainly I can't seem to form a well-defined, coherent vortical structure in this simulation. So the point of this experiment is just to demonstrate that this instability appears to be global in the vertical direction, and that means vertical boundary conditions or vertical disk structure might be an important factor in determining whether or not this instability can operate. So that's the end of this video. Just want to talk about some possible future problems. I think there is potential for these pseudo-spectral methods in linear stability calculations. So in the future, we want to maybe generalize these linear stability calculations to more problems, like, for example, a baroclinic equilibrium, so disks where the angular frequency depends on height. And eventually we need to include 3D self-gravity in these linear calculations. But I think a simpler starting point is probably just to think about what is the influence of vertical self-gravity, right? Because I know what horizontal self-gravity does. How does the extra vertical acceleration provided by the perturbations themselves affect the instability? On the numerical simulation side, one question to ask is, well, how do vortices evolve in three-dimensional self-gravitating disks? Because vortices are just overdense blobs, right? Now, I want to stress that these instability, this vortex instability, although they give you these overdense blobs, they are not gravitational instabilities. Now, there is a class of gravitational instabilities associated with disk structure. So that's the plot here. This is a disk planet simulation where I put in a giant planet in a self-gravitating disk, and the gap edges become gravitationally unstable through these global spiral instabilities. So these are not two instabilities. And as far as I know, there hasn't been too much work done on gravitational instabilities of this type. Certainly in the context of protoplanetary disks, there's only been a couple of papers. So it would be interesting to look into these type of gravitational instabilities in more detail, in particular to think about or explore whether these type of GIs could occur in the dead zone. Last thing I want to say is both the Zeus code and the Pluto code are MHD codes, and Zeus has a Poisson solver now, and I've been playing around with Pluto with the Poisson solver, so it's very tempting to go into the code and maybe just switch on MHD and think about magnetogravitational instabilities. So magnetogravitational simulations is certainly something to look forward to in the future. Although I've been thinking about protoplanetary disks, dead zones, planet gaps, a lot of the physics that goes on here is applicable with other origins of disk structure, I should say. So, for example, let's see, Saturn's rings has structures in them. The boundary layer between a star and a disk has structure in them. And also, black hole accretion disks have a epicyclic frequency that goes up and down, right? So that's structure. Okay, so that's the end of the talk. List of references. Now, all of the material I've talked about in here is summarized in these papers here. So have a look. Thank you.